Okay, guys, let's go. Before starting this session this morning, I want to talk a little about the midterm examination. We are here. We are on this week. Next week, we will be off. The week after next week, we will take the course normally. And after that, we will take the midterm examination. Okay. For the midterm examination, you can access to my site, download the midterm question sheet, do them at home, and when time comes, I will call each of you according to the list to face me, and I will ask several questions about your works, like what is this, what is that, how did you do this, how do you do that? Okay. If everything goes well, we will do in that way. You know, because due to the pandemic, maybe things can change. So normally we will take the midterm examination on this week. Are you right? So any question about the midterm examination?
Hi, teacher.
Yep.
Any limits about exercise or
question
whatever?
will be limited within exercises of the question sheet. I will ask things concerning about things in that question sheet in the 3 given exercises. Okay, if there is no more question, then I guess we can get back to our course. So, last week we were talking about Poisson's equation. So this one is Poisson's equation. The left side here is the acceleration of voltage with respect to position. Because we got here, you see the second order partial difference, the partial difference of potential with respect to position. And on the right side, we got the volume charge density and the permittivity of the environment. So we do the first example this morning here. I'm going to compute, give me 1 minute, the potential of this given field. For the first one here, for convenience, I change the name from A to V. And now I will find the Laplacian of the potential V here. To find that, firstly, according to the expansion of Laplacian in the rectangular coordinate system, I have to take the first order partial differential of V with respect to x. So this one here will be 2. And the derivative of x will be 1. Okay. And because we are taking the partial differential, so every other variable, y and z, they are constant with respect to x. So they must be intact in this way. Hiểu ạ? And from here, I can keep taking the partial differential because we have to find the second order thing here. And for the second order partial differential here with respect to x, you can see that because there is no more x in the first result here, so the second result here must be 0. And then we will apply the same procedure to the second variable, which is y. The first derivative here with respect to y will be, I guess, 4x y z to the power 3. Okay, because the Poisson difference of y square will be 4y. And then we will do this one more time using the just found result. Okay, so we got the second order Poisson difference of v with respect to y will be, you see, this one will be 4x z to the power 3. Finally, for the last variable z, the first derivative here will be 6 x y square z square. And then for the second order Poisson difference of this given potential with respect to the last variable in our current system, which is z, I got this one. I think the coefficient here should be 12, right? X y square and then z. Are you okay? And combining all of this, I will sum up the first, the second, and the third result to obtain the Laplacian of our potential. Sorry, not this. You will add 0 to 4x to the power 3 to 12xy squared z. Square. Say what? This is the final result. So you can see that, like our two previous operators, the divergence and the gradients. This one, the Laplacian here, is based mainly on the Poisson difference of something with respect to something else. Okay. The main difference here is that we have to take the second order Poisson difference instead of first order like the two previous operators. And please keep in mind that the inputs and the output of this operator are all scalar. They are numbers, not vector, like unlike the two previous operator. We can talk a little about this. The two previous operator here, the first one is divergence. For the divergence here, we consider the input and the output. What is this? The input of divergence, you see, is a vector. And the output of the divergence here is a volume charge density, so it must be a number, okay, or a scalar quantity. For the second operator, remember that it is a gradient. The input of this operator is a number because the gradient is a scalar quantity. But the output of gradient here is a vector because the output of this one, you know, is the EFI. It must be a vector. Now for our second order operator here, the Laplacian. You see, the input is a number because it is the potential, okay? And the output is also another number, is another number because the output is the ratio of the volume charge density to the permittivity. And And in the next coming chapter, you will know the last operator in, oh, what is this? Okay, so the optic mouse. The last operator you will know in the next coming chapter, is the curl or the rotation. Now for the operator, the last operator, can you tell me, can you guess the input and the output of the last operator?
Both vector.
That's right. By considering the three first operators, you can guess that the last one will be vector and vector for both the output and the input. Okay, sorry. Not this one. Okay, I did my job. Now your turn. I want you to do the part B or C or both if you can, but at least you have to do one of them. Okay? Okay, guys, 8 minutes. Okay. Then we have the Laplace equation. We start from Poisson's equation here you are. And if we let the right side to be 0, then here you are. This is the Laplace equation. These are Laplace equations in 3 coordinate systems. So you can see that Laplace equation is a special case of Poisson's equation, because the right side of this one is 0, so we come to a homogeneous differential equation. Okay. And the third section here, uniqueness theorem here, this one is not for you. You can understand that this theorem says that once we found the solution of Poisson's equation or Laplace equation, then that solution is unique. Okay, if it satisfies the given boundary conditions. Okay, finally one word that this one is not for you. So we can skip this. What is this? Now we do some examples about finding Laplace equation solution. We start from the simplest case. We suppose that our solution depends only one variable, x, for example. So what happens now? This is our Laplace equation, okay? But because v depends only on x, not on y nor z, so the two second terms, I'm sorry, the two terms here, this one and this one, will be 0. Are you right? Because v does not depend on y nor z. So this is, I think, the simplest second order differential equation. If you want to find the v here, you can find the primitive function twice. You take the integration for both sides twice, and you got this. Okay, you can verify this one by taking the first v twice, so it satisfies the given equation here. Are you right? For this solution, x is a variable, a and b, they are two constants. They can be found from the given boundary conditions. For example, we suppose that at the position x1, the potential field is v1, and at the position x2, the potential field is v2. Then, if you put this one and this one into our solution here, you can find the two constants, a and b. And you can find the full form, the specific form of the solution of this very simple Laplace equation. Okay. V1 and V2 here are called the boundary condition or the initial condition. In many cases, we can suppose that at some given position, the potential is 0, and without the loss of generality, we can suppose that at the position x is at the position of 0 for x, the potential field is 0. And at the second position, say D, for example, the potential field is V0. In that case, we have a simpler form of the solution of this equation. Here you are. Are you okay? Any question? So you can see that in this very simple case, a solution for a Laplace equation is not very hard to be found. Now, what is this kind of solution? You can imagine this case. This is a two-plate capacitor, and we knew that within the two-plate here, the potential depends only on the vertical direction, the vertical axis. It does not change when we go to the left or to the right, to the back or to the front of the screen. So it depends only on x, for example. So the solution here is the distribution of potential within the two plates of a two-plate capacitor. Okay. Now to prove that the solution here is correct, now you need to find the capacitor of this system. To find the EFI from the potential, we can take the gradient of this one, and we got this. And from the EFI here, we can find the electric flux density by multiplying this one to the permittivity of the dielectric of this capacitor. Okay, from this we can find the density. And at this position, because the density here is a constant, so you can see that at this position it is also the same like this. And remember the property of a conductor. This plate here is a conductor, and according to the first boundary condition between a conductor and a dielectric, we knew a long time ago that at this position, the density must be perpendicular to the surface of the conductor. Okay, so D here must be perpendicular to the surface, to the plates. So this one must be the normal component of the density. And according to, once again, the boundary condition between the dielectric and the conductor, we can come to the value of the surface charge density. Okay, this one, I repeat once again, is a boundary condition applied to this position. From the density here, you can find the total charge of one or two plates. Here you are. Why do we do this? Because I'm about to find the capacitance of this capacitor. By definition, remember that C will be Q over V. And here you are. And you can see that this result was found a long time ago in a chapter of dielectrics. Okay, and this one is correct. So we can conclude that our solution here is correct. Are you okay? I hope that you find this one not too difficult. All right, keep going. So that was story in the rectangle.
Can you come back?
Yes, sure.
I don't understand why the formula of V equal V0x over D.
This one?
This one? On the right. Yes.
Are you talking about this?
Yes.
This one is solution of the previous page. Here you are. V is V0x over D.
Oh, I see.
Are you right?
Yes, I see.
So this one is just a summary of the previous page. Okay. We suppose that if we suppose that V depends only on x, we suppose that at x being 0, v is 0, and we suppose that when x is d, v is v0, then here you are, this is a solution. Here's the next one. This is about the cylindrical coordinate system. We suppose that v depends only on the radius of the cylinder. Rho is the radius. So this is the expansion of Laplacian in this coordinate system. And because v depends only on rho, so we can remove the second and the third term from the right side, from the left side to have this. So this is you see once again a second order single variable differential equation. The full name is second order homogeneous single variable differential equation. And from this, if you take the integration both sides twice, you will come to the solution. Here you are. Okay. Then once again, we can suppose that we have two boundary conditions. We suppose that as the how can I say, as the cylinder having a radius of a, the potential is v0, and at the bigger cylinder, the potential is 0. So I got this. I find the two constant, and this is a simplified form of the solution. Okay. Right. So once we found this, please keep in mind that one is the potential difference. The potential fields of a coaxial cable. Okay, two coaxial cylinders. The first one has a radius of A, and the radius of the second one is B. Here you are. And V here is the distribution of potential in the space limited by two cylinders. Okay, similarly from this, you can find the EF5, the density, and we can find the capacitance of this coaxial capacitor, which was be found a long time ago. We can suppose that V depends only on phi, the angle, in the cylindrical coordinate system. Then by the very same way, you can see that V depends only on phi, so we can delete the first term and the last term from the left side to have this. And to find this, you can take the integrand both sides twice once again to have the solution. And similarly, you can find the form. Okay. The last story is about the spherical coordinate system. Let's suppose that V depends only on theta. So this is the expansion of Laplacian in this coordinate system. So we can delete, because the V depends only on theta, so we can delete the first one and the last one on the left side to have this. this, once again, you can take twice. You can take the integration for both sides twice to have the solution. You are. Okay, and what is theta? Theta is the angle of the inverse cone. Of the inverse cone. So we can suppose that this is one is the Earth. We can suppose that when the angle theta here is 90 degrees, we have zero potential, and at an angle of alpha, the potential is V0. So we got the simplified form here, V. And from V here, you can find also the EF5, and applying the boundary condition between the conductor and the dielectric, you can find rho s, the surface charge distribution on the inverse cone. Okay, and similarly, you can find once again the capacitance of this capacitor a long time ago. Okay. So to practice on this problem, I want you to do the second mid-class exercise. I suppose that V depends on R, or V depends on 5. I want you to choose this one or this one to find the solution of Laplace equation. Okay? All right, go ahead. Off you go. 6 minutes. Understand the question? I want you to suppose that V depends on R or depends on 5. And basing on your assumption, you have to find the solution of V. Okay, go ahead. Okay, people, it's time for a break. Enjoy yourselves. Okay, time out. Let's get back to work. For the examples of a solution of Poisson equation, we got here an example, and I'll ask you to read this by yourself. Okay. Session number 6 is in the session number 6 here, we expand our concerns from first order to a second, from a single variable to second, from single variable solution to a two variable solution. And in this case, we can apply the product solution or the separation solution. Okay, we suppose that V, for example, depends on X and Y. So this is the expansion of Laplacian in rectangular coordinate system. And because V depends on X and Y according to our assumption, then we can remove the last term here. Okay. So in order to solve for this second order differential equation here, we suppose that the solution here is the product of two other functions, X and Y. X here depends only on X, Y depends only on Y. So basing on this one, we can change the left sign here into this, you see. Because Y depends only on Y, so Y will be a constant with respect to X. So if we take the partial differential of V with respect to X, Y here will be a constant. So any idea for this page, guys? Okay, what can we do with this? We can transform this one into this, you see, very simple. And this is the idea of, from this stage, we can the key idea of the solution here. You can see that the left side depends only on X, right side depends only on Y, but they are equal always. Okay. Then from this remark, we can come to the conclusion saying that the left side and the right side, they must be all equal to the same constant. Here you are. The constant here, n first square here, is called the separation constant, because the name is separation because using this method, we separated successfully one equation into two other equations. The first one here is complicated because it is a two variable solution. I mean, we had to find the two variable solution, but this set here, they consist of two equations, okay? But each one here is a single variable, equation. So for solving for this set is normally much easier than that of the starting equation here. Okay. So this one is in the rectangular coordinate system. How can we solve for this and this? That is another story that we will not discuss here right now. Any question? Okay, now we move our attention to the cylindrical coordinate system. V here depends on rho and 5, so we can separate V into a product of two functions. This one and this one. Okay. R of rho and phi of phi. By the very similar way, we can come to the separation solution. Okay.
Teacher.
Yeah, go ahead.
I don't know why alpha power 2 plus alpha power 2 equals 0. Okay, I understand. So, sorry.
Okay, it's all right. Okay, the last one here is a spherical coordinate system. We can separate V here into two functions. Does somebody know how to pronounce this letter? What is this, guys? What is this? What is this letter? You don't know this? This one is uppercase theta, and this one is lowercase theta. Okay, so we break up V here down into the product of two functions, R of rho and theta of theta. Okay, and similarly, we got this. Please keep in mind that in this case, the separation constant is n times n plus 1, in which n here is an integer number. For the example of this method to solve for Laplace equation, you can read this example by yourself. Okay, it is pretty long, but it is not very difficult. So, because we don't have time, we don't have much time enough. So I let you to read this one by yourself. Okay. We come finally to the core idea of this chapter, numerical methods. We knew that solving for solving for Poisson's and Laplace equations are very, very difficult in a certain case, because we have to work on triple variable solutions differential equation. And in a certain case, sometimes it is impossible to solve for Poisson's and Laplace equation if we want to get the analytic solution of those equations. So a long time ago, they found another way to solve for these differential equations. They are numerical methods. Numerical methods means we use we do not take the integration, we do not take the differential, we use only addition, subtraction, multiplication, and division to find the solution. And the solution will not be a function like x plus y. The solution will be a series of numbers. Okay. So there are about 7 or 8 numerical methods. Due to the limitation of time in our course, I will introduce to you 2 methods. The first one is finite difference, and the second one is a finite element. For other numerical methods, you can find my textbook about the numerical method in electromagnetics. Okay, the first one is a finite difference. Finite difference method. This one is a two-dimensional Laplace equation. We suppose that V depends only on x and y. So, because V does not depend on z, so the left side here becomes something like this. Okay. Now we consider a region. In this region here, V does not change when we go to the left or to the right, we go to the back or to the front of the screen. Sorry, let me say it once again. In this region here, we suppose that V does not depend, V does not change when we go to the back or the front of the screen. V changes only if we go to the right or to the left, upward or downwards. So in this case, you see that V depends only on two variables, x and y. Now, instead of solving for this equation directly, I will do in this way. I divide this cross section here into many small and equal squares, as you can see here. The dimension of x square here is h. H here is called the incremental of the space. And now I will try to solve for this one approximately. Firstly, I will try to find the approximation of the derivative of v with respect to x at the point A. So instead of taking this one directly, I will take the difference. Okay, delta V here is a very small change of potential, and delta X here is a very small change of position. And by definition, delta X here is a very small, and or in other words, it approaches zero. But if we let that thing happen, then it will return to the starting equation, and that is not the story that I want to tell you. Instead of taking that, I will change delta X here into h. H here is a very small number, but it does not approach zero. Okay, so at the point A here, the change when I go from the red dot to the blue dot here, the potential changes an amount of V1 minus V0. And the distance changes by an amount of h, because I go from here to here. You see, the distance is h. Are you okay? You can think this one in another way like this. Let's suppose that I got a curve. This curve here represents the dependence of V on x. And this point here is A. Okay. Let's suppose this one is x. And this axis, for example, is V. And we have to find the difference at the given point A. By definition, the derivative of V with respect to x at A is the tangential of the angle between the tangential line and the x-axis. Okay, this is tangential of this angle. But because finding tangential of angle here directly is very difficult, so instead of taking the tangential, we find the angle of this straight line. Here you are. Okay, so this one is the tangential line, and the right side here is this line. Sometimes they are the same. So the numerator here is a difference. And because the difference here does not approach 0, so it is a finite difference. That explains the name of this method, finite difference. So do you have any question? Similarly, for the for delta V over delta X at the position C, we can replace that by this approximation. Okay, when I go from the blue dot to the red dot, the potential changes by an amount of V0 minus V3, and the distance changes by an amount of H once again. Okay. This one is the first order differential, but the equation here is second order one. So we try to approximate the second order differential by this one. The second order differential is a differential of the first order differential. So we got this. Combining this, and this, we got this one. So this is the first term, the approximation of the first term. In the very similar way, we can approximate the second term like this. Combining all of this, finally, we come to the core idea, the fundamental of this method. Here you are. This one says that the potential of any point is the average value of the 4 surrounding points. Now I will try to extract some comment. I will try to give some comments for this equation. Firstly, you can see that this one is just an approximation. This approximation will be more and more exact, more and more accurate if h here is smaller and smaller and smaller. In the best case, if h here is a 0, so the 4 surrounding points will be V0, and this one will be equal, because in that case we got 4 V0 over 4 will be V0. Okay, so the first comment is that the smaller the value of h, the more accurate the result. Okay. The second comment here is that this approximation holds if and only if the four surrounding points here are equally separated as equally distant from the center point. For example, if V1 was here, then this one would be no longer correct. Are you okay? I want to tell you that the 4 surrounding points here must be symmetric about the center point. Otherwise, this one might not incorrect. Might not be incorrect. And one more thing, it is that our formula here, let's say that we compute in a diamond formula, diamond way. By the very similar way, we can prove that we can apply this one to the square computation. Okay, the 4 surrounding is the 4 nodes of this square. So there are 2 ways to apply this formula, the diamond or the square. Okay, Now, please tell me which one is better, the diamond or the square? Can you guys tell me? Which one is more accurate?
Diamond method.
Yeah, that's very good. But why? Why diamond is better?
Because the distance is smaller than when we take as a square.
Yeah, excellent. You see, for the diamond, the distance is from here to here, which is h. For the square, the distance will be square root of h. Square root of 2 multiplied to h. So it is about 1.4 times greater than the diamond. And therefore, according to our first command, when the distance here is greater, the accuracy is smaller. Okay. Okay, that's very good. Are you all right? Any question here? So, two main ideas. The first one is that the four surrounding points must be symmetric about the center point. And secondly, there are two ways to compute to apply this. The first one is the diamond, and the second one is the square. And the diamond is better than the square. Okay. Now we apply that idea to our first very simple example. This is a cross-sectional view of a system. The system here consists of a U-shape, a meter U-shape. So this one is a conductor and a lid, a cover. You know what lid and cover? This is the lid of the U-shape. The lid here is also made of meter. So this one is another conductor. The potential of the cover of the lid here is 100 volts, and the potential of the U-shape here is 0 volts. Between the lid and the U-shape here, there is a very thin air gap. The air gap here is to prevent the two conductors here, to prevent the two conductors here from being equal by the potential. So the cross section of this U-shape here is a square, and we suppose that our system here extends forever to the front and to the back of the screen. So the potential here does not depend on Z, it depends only on the vertical axis and the horizontal axis. So it is a two variable solution. To find the distribution of potential within the U-shape, within the system here, instead of solving for Laplace equation directly, we here divide the region here into 16 squares, 16 equal squares. And so we have to find the potential at 9 nodes, VA, VB, VC, D, E, F, G, H, I. Okay, and we are about to find those potentials by applying the fundamental formula of the finite difference method. Now, if I apply this one to this node A, I got this. VA will be VD plus VB plus 100 plus 0 over 4. Or in other words, we got this. Please keep in mind that a conductor is an equipotential surface. So every point on this surface will have the same potential, which is 100. Okay. Are you all right with this? Now, can you help me about the equation for the node B? What will be that? Can you help me? It will be 4B, 4VB equals to what?
100. Yes. Float VA.
That's good.
Float VE and float
That's
VC.
good. That's very good. Okay, 4 times of VB will be 100 plus VA plus VE plus VC. You can say that into 100 plus VD plus VF plus V100. I'm sorry, plus 100. But we knew that a diamond is better than a square, so in this case, I apply the diamond. All right?
Yes.
Thanks. That's very good. Similarly, you can find by yourself the equations of the 8 of 7 remaining nodes like this. Okay. So what do we do now? You see that finally we come to a set of 9 equations and 9 unknowns. Solving for this, you can find a solution. Here you are. That's it. The problem here is that for many guys, solving for a set of 9 equations is a very hard work. Okay, but anyway, this is the first method. Let's say that this one is a matrix method. Are you all right? Any question?
Excuse me, teacher. I have
Yeah.
a question. If we use diamond method, and can we use diamond method and square method together to find those?
Yeah, you can do that. You can do
Okay.
that. But in that case, I'm not sure that the result is correct. It can be written off, be off written from the precise answer. So in the best case, you should use diamond all the time.
Okay. Okay, thank you.
You're welcome.
This method has many function, many many equation. So we quite hard to find the result.
Yeah, I got that.
Yes.
That's what I told you. So
I think we should find VA.
okay.
VA and we can find VE at first.
Okay.
By use diamond method.
That's very good. Mr. Hoàng Văn Đạt, right?
Yes.
You are very intelligent. That's the key idea of the second method I'm going to tell you now.
Yes.
Very good. You have an, how can I say, we have the genie of an engineer, I think. Okay, so any other question for this method? Are you right? So, according to Mr. Hoàng Văn Đạt, we should not apply this method because if you try to do this, you have to deal with the solution of many equations, many unknowns. We try to apply the second method, and we do that exactly like the way Mr. Đạt told us. We start from the middle point. Okay. For the middle point here, normally we should take, we should rely on this node, and this node. But the problem is that so far we do not know the potentials of those nodes. So we should expand our concern to 4 further nodes. This one, this one, this one, and this one. Okay. So we got 100 plus 0 plus 0 plus 0 over 4 is 25. Are you okay? And then we can keep going. For the blue dot here, now we're trying to find its potential. If we apply the diamonds like this, plus this, plus this, plus this, then we need this one and this one, but we do not know so far the potential of this node and this node. So instead of using the diamond, now I have to use the square summation. Okay, it will be 0 plus 25 plus 100 and plus the possion of the air gap. How can we find the possion of the air gap? Now please take this one down to your notebook. The possion of the air gap will be the average value of a two neighboring possion. So the possion of the air gap here will be 100 plus 0 over 2, which is 50. Okay. So finally, the possion one will be 100 plus 50 plus 0 plus 25 over 4. And we found here the possion of this node. Are you all right? Any question? So, due to the symmetry, the vertical symmetry of the system here, we can project our just found result here onto this point, this node, I mean. Okay. And then I will try to find the possion of the green node, this one. Can we apply the diamond here, guys? Can I use a diamond? No, because so far we do not know the possion of this node and this node, so we have to use the square. It will be 25 plus 0 plus 0 plus 0 over 4, which is 6.2. And we process one symmetrically to the opposite node to have this. Are you okay?
Yes.
And then we need the pink node. Now can I apply the diamond? Yes, because I knew this and this. So now I can use the diamond. It will be this plus this plus this plus this over 4 in here. What? So can I process this one onto this node, guys? Can I copy this one to this node?
No.
No. Why not? Because the system here is not symmetric about the horizontal axis. Okay, so we have to compute this. But firstly, we try this. Now we can apply the diamond. Because we knew the 4 surrounding nodes. So it will be this plus this plus this plus this over 4. 18.8. Okay, and we process one into this. And the last point here will be 25 plus 6.2 plus 0 plus 6.2 over 4. Okay, and finally got this. Any question? This is the first step because everything, you know, every figures that we found here, they were all based on the starting points, the starting value 25. And this one is, I'm not sure this one is correct because we found this one when we take the average value of two of the 4 two far nodes, this one, this one, this one, and this one. So we have to modify these solutions. How can we, I mean, we have to modify these results. How can we do that? we have to repeat the process. That's why the name for this method is the iteration. Do you know that word, iteration? Yeah, we can solve for this one in MATLAB. The problem is that in the final examination, so far you are not allowed to use laptop. So second method is iteration, or repeating method. Now I have to modify this one a little. This formula here, you know, we found this from the square summation. Okay, 100 plus 50 plus 0 plus 25. Now I try to modify this by applying the diamond summation. Okay, sorry, the diamond summation. I will take 100 plus 0 plus this one over 4, and you can see that the result here changes a little. Okay, so I change this one from 43.8 to 43, and similarly we got this. And now I will try to recompute this one. This one, you see, was based on 43.8, but this one is no longer correct. This one should be 43.0. So I change this one a little. I change this one from 43.8 to 43, and you see, finally the result here is modified a little. Get the idea? So we repeat our method here for every remaining nodes, and finally we got this, for example.
Teacher.
Yes.
Excuse me. Each one point had two value of voltage, potential.
Okay.
Oh.
So theoretically, we will take the lattice, the results of the lattice step. Okay, because it can be proved that the more step we take, the more accurate the result that we obtain. So if we have to stop here, we will take, for example, 80.6 instead of 80.8, 18.8. Okay.
Excuse me, teacher.
Yeah.
So, if we modify one point, so do we need to modify all the points here?
Yeah, we have to modify all points.
Okay, by using the previous one, right?
Yeah, by using the more reliable results of the previous step.
Okay.
Like there are two ways. The first one is that instead of using the square, you can use the diamond, and instead of using the starting value, say 43.8, you can use the new updated value like a 43. Two ways.
Okay, so to modify 43.8, we use 53.2, and then we modify to 53.2. We use the modified value of that point, earlier point, right?
Yes, right. We use the just found new value.
Okay. Thank you.
You're welcome. And you can repeat this one forever if you want. You can modify once again, like for the blue dot here, instead of using how can I say, 53.2, we can use a new one, the just found value 52.8, to change this one into this. Okay. Similarly, you can rely on the new summation, the diamond, or you can rely on the just found value of the previous step to modify the new one in the new step, like this. The question is that how many steps do we have to repeat? Do we have to do this forever, or in other words, when do we stop? The answer here is that it depends on the requirement of the exercise. Okay, and what is the requirement? It is the absolute error, delta V. To compute the absolute error here, you have to find the maximum difference between two steps of one node and for every node. For example, delta V between the second step and the first step will be this. You see, I will take the absolute value, okay? The difference between the first and the second here will be 0.8. This one will be 0.4, 0.8, 0.2, 0.1, 0.2, 0.8, 0.4, 0.8. So it will take the maximum value of the absolute value. Okay, so delta V between the second method, the second step and the first step is 0.8. Are you okay? The terminology here is the absolute error. I will type it here. Give me 1 minute. So computing the absolute error here is very important if you want to apply the iterative method. I mean the method number 2. So any question for finding delta V? So can you help me to find delta V between the third step and the second step? What is that, guys? Just compute, okay. Between this and this will be 0.1 because 43 minus 42.9 will be 0.1. So for this node, it will be 0.1. For this, it will be 0.1, 0.1, 0.1, 0.1, 0.1, 0.1, 0.0, and 0.1. So we take the maximum value of the absolute value. So delta V between the third step and the second step is 0.1. Okay. So for an exercise, it will be given beforehand this value. For example, the requirement of this exercise is 1 volt. So can we stop after the second step?
Yes.
Yes, because delta V is 0.8, which is smaller than the threshold 1 here. So we can stop. But if the requirement, the absolute error is 0.5, can we stop at the second step? No, because 0.8 is greater than 0.5. Are you right? And can we stop at the third step? Yes or no? Yes, because remember that the absolute value, the absolute error between the first step and the second step, we found that it is 0.1, and 0.1 is smaller than 0.5, so we can stop at the third step. Can you get this idea? You right?
Yeah.
I think this is not very difficult, but you can ask me anytime. Are you right with this? So if you want to use the iterative method to solve for this kind of exercise, you have to check the absolute error and have to verify whether it satisfies the given condition, the given criterion. Okay. Yes. On my page there is An error, it should be S square. Thank you, Mr. Nguyễn Thái Nguyễn, right? Yeah, you are right. I will modify that. Thanks. I mean that on this page. Give me 1 minute. This one should be S square, not H. Sorry for my typing error. Okay, this one is S square. Are you right?
Yes.
Okay, then that's all for today. Next week we will be off. See you the week after next week. Goodbye, guys.
Goodbye, teacher.
Goodbye, teacher.
Goodbye.
Goodbye, teacher.
Bye bye.